Hey everyone, on this occasion we will study the main operations that we can perform between words. The first of all is how to represent the number of occurrences of one word within another. So the idea here is that if we want to compute the number of occurrences of a given word, for instance the word X, where X is a word that is different from the empty word. X is not the empty word. So we want to compute the number of occurrences of this word X in another word. For instance, let us call this other word W. So how do we represent the number of occurrences of the word X in W? Well, the way of doing it is the following. We take the W word. So in this case, our word is W. We write two vertical bars. And then as a subscript of this expression, we write X, like this. With this expression, we are representing the number of occurrences of the word X inside the word W. For instance, on the previous lecture, we were working with the alphabet sigma, which we defined to be the alphabet AB. We had two possible symbols, the symbol A and the symbol B. So we were working with this alphabet, and from this alphabet we had built some words. Some of these words could be, for instance, the word AB, also the word BBB, and for instance another one could be the word A. Now sure, we here, if we want to compute the number of occurrences of the word A in the word AB, so how would we do it? Well, first of all, the idea here is that we write the word W. In this case, the word W is the word AB. So we write here the word W. Then we write this both vertical bar symbols, these two pipes. And then as a subscript, we write the word we want to compute the number of occurrences of. So in this case is A. So we just write A in here like so. So this expression is computing how many A's we have in the word AB. If we analyze the word AB, we can see clearly how we have only one A. So the number of occurrences is equal to 1. If we had another word, let us suppose that we have now the word ABA, AB. So now the word W is this word in here. So now if we want to compute how many occurrences we have of the word A inside the word W, notice how in this case X is A, and now we just denote in the same format as we have here. And so we write W. In this case, it is the word AB, AAB. We use the two vertical bars. And then as a subscript, we write the X value. And in this case, it is the word A. And so this expression represents the number of occurrences of the word A within the word AB, AAB. And so now if we count how many A's we have in this word, we can see we have 3. We have this one, and this one. So we have 3 occurrences, and thus this expression is equal to 3. So this is how we represent the number of occurrences of a word within another. Very well. Let us now suppose that we have a new alphabet that consists of 2 symbols, the symbol 0 and the symbol 1. And so let us suppose that we have the word W, which is the word 0, 1, 1, 1. Consider that we have this word. And then we have another word, let us suppose here the word X, which is the word 1, 1. And so now we want to compute how many occurrences we have of the word 1, 1 within this word. And so the following concept that we're going to explain now is very, very important. When we compute the number of occurrences of this word inside this one, that is in this way, right? Here we have the word W, here we have the word X. And so look, how many elements we have of 1, 1 in here? Well, if we analyze this word, we can see how this is the first occurrence of the word 1, 1, but then we have another one. And so basically with different colors, this is the first occurrence, and this is the second occurrence. So we have here 2 total occurrences of 1, 1 inside this word. And so we just write 2. Let us study now another important concept in words, which is the subword, also called the factor of a word. Let's see how we can define this concept. In fact, let us study this concept with a series of instances to understand it. Let us again consider that we have the alphabet sigma with the symbols 0 and 1. And so we have this binary alphabet. And so here an important notion is that the word 0, 1, this word is a subword or factor of word of the word 1, 0, 1, 1. Why so? Well, here as we see, the word 0, 1 is a subword of the word 1, 0, 1, 1, because here we see that we have an instance of this word within this word. Now, in the context of formal language theory, a subword of a word can be categorized as either a prefix, a suffix, or an infix based on its position within the word. For instance, a subword is considered a prefix if it appears at the beginning of the word. For instance, the word 0, 1 is a subword that is a prefix of this word in here, the word 0, 1, 1, 1. And we know this because this subword takes place in this word in here at the beginning of the word. So essentially, a subword is a prefix of another word if the other word starts with this subword. In language theory, a subword can also be an infix. An infix is a subword that appears within a word, but not at the beginning or the end. And so we can see how this is precisely this case in here. We can see how 0, 1 appears in this word 1, 0, 1, 1 in this place, which is not the beginning nor the end. So 0, 1 is an infix of the word 1, 0, 1, 1. A subword can also be a suffix of another word. This happens if it appears at the end of the word. And here we can see a very simple example. We can see how the subword 1, 1 is a suffix of this word 0, 1, 1, 1 because the subword appears at the end. Now, another important aspect of subwords in language theory is that if we have the empty word lambda, this word is a subword of any word by definition. So always the empty word is a subword of any word. Since any word that we can think of W will always contain the empty word lambda. And finally, a last property of subwords is that if we have a word W, this word is considered to be a subword of itself. This is trivial since every word is a subword of itself because it contains itself as a subword. Alright, the next idea that we're going to consolidate is how we can represent the ith symbol of a word U. In this case, imagine we want to get the ith symbol of the word U, then we just represent it and denote it in this way. We write the word U and then between square brackets we write this position I. Now at this point, students that are used to working with arrays or vectors will be familiarized with this notation. So to represent how to access the ith symbol of a word, suppose we have a word U. To access the symbol at the position I, we just write u, and between square brackets we write this position, this index I. So what's important here is that in words, this index value, this index I, is between 1 and n, where n is the length of this word. And so by definition, n is the length of this word, in this case the word u. Remember that we represent the length of a given word in this way, as we already saw before. And so whenever we write an index here, it must be between 1 and n. For instance, if we are working with the alphabet 0 and 1, if we're working with the binary alphabet, and then we have the word, for instance, 1011, which is the word that we're working with. And so then if we want to compute the third element of this word, we just denote it like so. We write the position of this element between square brackets. And as we see, since we start with 1, this is going to be the position 1, the position 2, the position 3, and the position 4. So we are now accessing the third element. This is the I, the index. And so we can see how it is this one. And so we can just write 1. As easy as so. The same, for instance, if we have this word and we want to access the symbol at the position 2. We can see in this case how the second element is this one, so we just write 0. So as we see, to represent the ith symbol of a given word, it is very easy and simple to do. Good, let us study now the operation of concatenation between words. So we have two words, for instance, or more. What is the result of concatenating them? So in order to explain concatenation, let us suppose we have two words. We have the word u and the word v. In order to make the concatenation of u with v, we represent it with u dot v. This is the concatenation of u with v. The concatenation of u with v is basically the juxtaposition of u followed by v. Let us take a look at an example so we can comprehend this deeply. Let us first take a look at the base case. When we are concatenating the empty word, let us suppose that we are concatenating a given word u with the empty word lambda. Well, the result of this, as it is the juxtaposition, it is the formal definition of concatenation. Then, when we concatenate u with the empty word, we are going to obtain the word u, since the empty word does not contain any single element. The same goes when we concatenate the empty word lambda with another word u. The result is also u. So here the idea is whenever we concatenate the empty word with another word, the result will always be the other word. In fact, this is a property called the neutral element. The empty word, the lambda word, is the neutral element of the concatenation. Let us consider now that both words that we are concatenating, both words u and v, are not the empty word. So let us suppose that the word u is the word of the symbols a1, a2, until a7, and then the word v is the word with the elements b1, b2, until the symbol b sub m. Here we are just using a different symbol m from the symbol n to indicate that the length of the word u can be different from the length of the word v. Notice how n is the length of the word u and m is the length of the word v. These two values can be different or they can also be equal. In both situations, the concatenation will always be possible. What is essential when concatenating two words is that they both belong to the same alphabet. So here what we are supposing is that each symbol of this word u, each A sub I belongs to the alphabet sigma, and in the same way, each symbol of the word V, each B sub j, belongs to the same alphabet sigma. And also, the I is between 1 and n, where n is the length of the word U, and j is between 1 and m, where m is the length of the word V. So when we concatenate U with V, what do we get? Well, we just look at the formal definition. It is the juxtaposition of U followed by V. So this is going to be a word. The result of concatenation is a resulting word, where first we are going to have the U, and then followed we are going to have the V. So we first have the U until its last symbol, and then we have the V. So this is the result of concatenating U with V. So now let us take a look at some property of the length of the concatenation. That is, what if we want to compute the length of this new word? As we mentioned, the result of concatenation is a new word. And so if we want to compute the length of this new word, it is very simple. We only need to sum the length of one word plus the length of the other. So as we know in this case, the length of U is n, and the length of V is m. So the length of this new word after the concatenation is going to be n plus m. Let us now have a look at some properties of the concatenation. The first one is that the concatenation is associative, in the sense of if I have three words, U, V, and W, if I concatenate U with V and then the result I concatenate it with W, this is the same as, and it is equivalent as first concatenating V with W and then concatenating U with the result. So the concatenation is associative. Now another very important property is that the concatenation is not always commutative. In the sense of if I concatenate a given word U with a word V, this does not have to be equal to concatenating V with U. This property is very easy to show. If we have that the word U is the word 1, 0, the word V is the word 0, 1, then when we concatenate U with V, we get U followed by V, like this. And this is not equal to concatenating V with U, because notice that if we concatenate V with U, we get 0, 1, 1, 0, and this is different from 1, 0, 0, 1. So we conclude that the concatenation operation does not verify the commutative property. The final operation that we are going to see on this lecture is the operation of the power of a given word. That is, suppose we have a word W and we want to compute the nth power of this word. We represent this power in this way. We have the word W, which is the base, and then we have the exponent n. Now, what does it mean to raise a word to a power n in language theory? Well, this operation is defined in the following way. We can define some cases. First of all, let us begin considering the case where n is 0, that is, the exponent is 0. Well, when we compute W raised to 0, the word W raised to 0, well, then this is the same as saying 0 occurrences of the word W. So we have that this is equal to lambda, to the empty word. Then, when the n is greater or equal than 1, by definition, when we compute the nth power of this word, this is equal, by definition, to W concatenated with W raised to the power of n minus 1, which is noticed in fact equal to W raised to the power of n minus 1 concatenated with W. To visualize this, let us just suppose we have the alphabet AB, and so suppose that we have a word W, which is the word AB, and we want to raise W to 3. Well, since the word w is equal to ab, this is the same as raising ab to the power of 3. And so if we apply the definition, this is equal to the word w, which is ab, concatenated with the word w, which is ab, raised to the power of n minus 1. So notice how the value of n here is 3, so n minus 1 is 2, like this. And notice how this at the same time is equal to ab concatenated with this. And here if we apply again the definition, now the value of n is 2, right? So this is equal to the word w, which is ab concatenated with the word w raised to the power of n minus 1. So since in here n is 2, n minus 1 now gives us 1. So we have ab raised to 1. And so here finally we apply again the definition. Now the value of n is 1. And so this in here concatenated with the word ab raised to n minus 1. So since n is equal to 1 now, n minus 1 gives us 0. And notice that we have reached the base case, since we know that whenever we have a given word w, and this word is raised to 0, this is equal to the empty word. So this expression can be rewritten as lambda, as the empty word. And so notice how we have reduced the operation of raising a given word to the power of n to an operation of concatenation. And as we concatenate this, we have the final word ab, ab, ab. And notice that computing the nth power of a given word is very simple. We only need to repeat the occurrences of the word n times. So since here the exponent is 2, this is just the word abb 2 times. An important property as well is that whenever we raise the empty word to any power n, this is always going to be equal to the empty word for any value of n greater or equal than 0. By definition. Very well, with this we end this lecture on the main operations between words. On the following lectures we are going to see many more fundamentals on language theory, and in particular, on the following lecture we are going to see the concept of language.